Today we'll be talking about the thermochemical storage of ammonia by Brett Schumacher and John Bernard. Solar power has great potential as a renewable energy source. However, the sun isn't always shining and energy demand is always changing. For solar to become a principal source of energy in the future, it will need to be coupled with cheap and reliable ways to store enough energy to power the electrical grid when demand exceeds solar energy production. We propose to solve this intermittency issue using well-established and cheap industrial chemical processes, namely the thermochemical dissociation of ammonia and subsequent ammonia synthesis.
The setup of this technology is comprised of a three-part closed-loop system. Upon charging during the daylight, solar concentrators, such as mirrors or heliostats, will heat up an endothermic reactor that contains liquid ammonia. The energy harvested from these solar concentrators is used to disassociate this ammonia into its constituent gaseous parts, gaseous nitrogen and gaseous hydrogen. These two gases are cooled down and pumped into a storage tank where they are stored until the demand requires that these energy is harvested again. To harvest this energy, these gases are pumped into an ammonia synthesis reactor where, along with a catalyst, can be recombined into its original ammonia state. This is an extremely exothermic reaction, and the heat captured from this recombination is used to do work to generate electricity. The recombined ammonia is then pumped back into the same storage tank where it can be disassociated again, hence a closed-loop system. The status of this technology is currently at lab scale, with lab-scale reactors and lab-scale storage tanks. The solar-to-energy or ammonia dissociation efficiency is currently at 25%, which is comparable to current solar-to-storage technology such as PVEs and PV to batteries. The ammonia synthesis, or the discharging step, is at around 81%, so we can recombine the gaseous phases back into ammonia pretty efficiently. What's really promising about this technology is that there are established pathways for scaling using current industrial techniques. The synthesis is using Haber-Bosch, which is really well understood, and the dissociation using concentrated solar arrays is already widely used. Finally, the storage can be used the same way as hydrocarbons are currently stored in gas caverns or old mines.
Like all technologies, there are advantages and risks. One advantage is that there are no side reactions, so conversion efficiencies tend to be high. Additionally, there is a natural phase separation at ambient temperature, so one tank can be used for both products and reactants, reducing capital costs. Finally, these chemical processes are already well understood at industrial scales, and much of the infrastructure and supply chain problems have already been worked out. A major concern for the system is finding cost-effective storage solutions for chemical components, which need large volumes of high-pressure storage at scale. Additionally, the system cannot be distributed, so large amounts of land will be needed to fit the solar concentrator array, chemical storage, and ammonia synthesis reactor. Furthermore, initial synthesis of ammonia is not a completely green process, and thus the leakage of chemical components will both reduce round-trip efficiency of the system and require more energy to make replacement feedstock.
In conclusion, this technology has the potential to solve current solar intermittency issues at comparable efficiencies and cheaper costs than that of photovoltaic plus battery systems. This tech is also easily scalable using current infrastructure of hydrocarbon fuels. Though promising, there are some risks to also be aware about. This technology is static and will only be able to exceed at large scales, which will require very specific geographical parameters, such as sufficient storage, land area, and sunlight in the same place. Currently, there is a startup working to develop a pilot-scale plant to continue to optimize this tech for the best efficiency at the best price point. Thank you for listening.